Let's begin. So today's review lecture is Manus Visser from the University of Cambridge, and Manus going to talk about quantum physics.
Okay, thank you very much for inviting me. This is a really exciting topic on which recently there has been a lot of development, also on quantum gravity in de Sitter space. And so I would like to discuss today with you these four different aspects of de Sitter space. So first I will describe the classical geometry of the de Sitter space, but if I'm going too slow, then please just tell me to speed up if you already know this. Then I will review thermodynamics of de Sitter space, and in particular a kind of conceptual question about the thermodynamics related to the minus sign as the first law. And then thirdly, I will discuss some recent developments on how to interpret de Sitter entropy. And finally, I will have some brief comments on holography for de Sitter space. So to begin with, what is de Sitter space? It's the maximally symmetric spacetime with positive curvature. And equivalently, it's a solution, maximally symmetric solution to the Einstein equations with positive cosmological constants. Now, de Sitter space is not only theoretically interesting because it's maximally symmetric, it's like a ground state in general relativity. It's also very relevant for our universe, partly so for two reasons. So de Sitter space is exponentially expanding. We have two phases of exponential expansion, namely in the early beginning of the universe, to inflation. And so the scale invariance of the cosmic microwave background is direct evidence for late time de Sitter phase. And the second phase is the late time expansion. So from observations of supernova, we know that the universe is accelerating, exponentially accelerating, and the energy density is dominated by the cosmological constants. And so if we assume that this exponential expansion just continues, then all matter and radiation in the universe will dilute and will be dominated by the positive cosmological constant, and hence there will be pure de Sitter phase at asymptotic late time. And actually, there is a theory called the cosmic null theory by Walt from 1983 that roughly states that in most cosmological scenarios, as time evolves, all matter and radiation will dilute and will be approaching asymptotically a locally de Sitter geometry. So just like you have a Noether theory for black holes, you also have it for cosmological spacetimes, and then you have de Sitter space in the asymptotic future. Okay. So this was the motivation for why we're studying de Sitter space. Now, let me draw the Penrose diagram. And let me also say that the isometry group of de Sitter through O1, D, which is the Lorentz group in D+1 dimensions, and it's a non-compact group. And so let me give you some coordinates. cover the entire geometry. So global coordinates, the metric in global coordinates, the metric takes the following form. Okay, so constant time slices, constant tau slices are sphere d-1 spheres. So these time slices are d-1 spheres at times time runs up, and it starts out infinitely big, and then it contracts to a minimal size of length L. So the sphere contracts, and then it expands again. And so this is this is past infinity, and this is future infinity. And these boundaries are not really boundaries; they are the poles of the sphere. So I'll call this the north pole, and this the south pole. Okay, and right. So the topology of the Sitter space is and R as. And also note that this metric depends explicitly on time, so there is no global time-like hidden vector. This will have important consequences that we'll see later. Okay. Now, there's one peculiar feature of the Sitter space, and that's that no observer has access over the entire space. So if you're sitting at the North Pole, then you can receive signals from this wedge this way, and you can send signals like this. So you can receive signals from this triangle, and you can send signals to the triangle. And the intersection of those wedges, O plus and O minus, that is the, so this is O minus, O minus, and plus. So the intersection is called the static wedge, or causal diamond. And you have two of those, the northern causal diamond and the southern causal diamond. So that is the region that is fully accessible to an observer sitting at the North Pole, or someone staying inside this wedge. So it can receive signals and send signals in this way. Okay. So the coordinates for the static wedge, the static coordinates formula. So at each point there is d minus 2 here, and the constant here. Which is the statement that I made before, that there is no global. These isometries are incompatible. Jitter entropy, and size is compact, the charge is actually vanished. The Hamiltonian on compact geometry in gravity just vanishes. So that also seems to be inconsistent with supersymmetry in the system. However, there are some exceptions or ways to go around this idea. And one is to have superconformal theories in the jitter. And in that case, you can use a global conformal time-like Killing vector. So that does exist. And then you kind of invade this argument. So this was is based on work by Manus, Friedman, and Mahoney from 2014. And another evade is to consider supersymmetric higher spin theories in the system. And well, in that case, the permission conjugate does not satisfy a different rule. And then this argument doesn't apply. So there are supersymmetric versions of higher spin theory, which work in the Sitter space, and also people have considered DSCFT with higher spins. And people have generalized that, including supersymmetry. So there's work by Thomas Hertog, Thomas van Riet, and Matsu Yeli from 2018, which is about a supersymmetric DSCFT, but then being two higher spin points. Right. And actually recently there was a paper on two-dimensional, so 1 + 1 dimensional supergravity in the Sitter space by Dionysios Annos, Friedrich Luhmann, and Jim Lee. And actually in that case, the isometry group of DS2 is the same as the isometry group of ADS2, which is in that case you can have supersymmetry. That's global. No, you can just do globally. Yeah. Yeah. So there is more possible. There's actually more possible than you might.
In general, the absence of global supersymmetry. What are the implications for programming?
Yes. So there are the Zitterfagua in supergravity, but they are unstable with ghosts, and that's like a manifestation of this fact.
The DS2 is the one that is
Yeah. I mean, it has some similarities with the other questions?
people are trying to make it visualization in the system is one analytic configuration. This really not happen. So they can afford this and this is another reason to the violencia information.
No, not really. But I suspect that you would run into this problem. I mean, yeah. I think in the end you want to do that. Yeah. Do you know maybe anyone system? I see. Now I want to discuss thermodynamics. So as we saw, the Sitter space has a cosmological horizon and has an associated thermodynamics associated with, just like black hole horizon. So cosmological horizons share some similarities to the black hole. So what is the evidence that we have for the thermodynamics of the Sitter space? Well, first of all, you can do QP in a fixed Sitter background. So and try to describe the Hawking effect. Secondly, you can derive thermodynamic laws for cosmological horizons. And thirdly, you can derive the Sitter entropy from Euclidean pair partition function. So let me start with one briefly. So if you consider the Sitter invariant Dracula, then actually this is not unique. There's very many called alpha Dracula. But if you now restrict the vacuum state such that the propagator only has singularities on nulls or on between 2 points, X and Y. If these 2 points are null separated, then the vacuum state is unique, and it's called the Bunch-Davies vacuum. So
You know, certain yourself with the static back.
no, this is just for a global Sitter. Yeah. So these are all of that, you know. But then we restrict. Okay, so if we demand this, then the vacuum state is the so-called Bunch-Davies vacuum. This is equivalent to the Euclidean. So you can prepare the states in Euclidean signature with the path integral, and if you do that, then you prepare precisely the Bunch-Davies state. The Euclidean particular here, direction. If you prepare a state of T0 in this way, you prepare this Bunch-Davies vacuum state. Now, very important is that if you restrict So this is a global state. And if you then restrict to one static patch, then the state is thermal. So when restricted to one static patch, then you get a thermal density matrix. So let's say the north, so density matrix associated to the northern static patch. And this means you trace out over the southern static patch. Then you get a thermal state or a Gibbs state in this way, where the Hamiltonian is the Hamiltonian generates the time within the static patch. And it takes this form. So psi is the killing vector of the static patch, the time the killing vector of the static patch. And beta here is that's the inverse temperature, and it's given by kappa over 2 pi, where kappa is the surface gravity associated with the horizon. So one of the definitions of kappa is this. Evaluated at the horizon. So here, maybe I should here. So psi is the spinning vector. Psi is ddt. So actually, the normalization of psi is arbitrary. So if you take psi as ddt, then psi of psi is -1 at the center here, and then psi is ddt, and that means that kappa is 1 over L. So with this choice of killing vector, you get 1 over 2 pi L, where L is the curvature radius of the Sitter space. But in principle, you could have normalized it differently with a different, so some constant here, and then kappa also changes. But with this choice of normalization, you get 1 over 2 pi. And so this is the generalization of the Bissignano-Wickman theorem in Minkowski space. So in Minkowski space, if you have the Minkowski vacuum, which is invariant under the Poincaré symmetries, and you restrict to the Ritter wedge, so you restrict to the wedge, then the state is thermal, where beta is then and so this Bissignano-Wickman theory applies to any Lorentz invariant quantum field theory, and it's very general and follows from an algebraic approach to quantum field theory. Right. So actually, any geodesic in the Sitter space is related by the Sitter isometries. So any geodesic observer in the Sitter space will observe this temperature. And this was actually found in 1975 by Napi and collaborators. But then also independently later by Gibbons and Hawking. And there's one fun what other fun facts I would like to tell you. If you consider an accelerating observer, so an observer that stays at some constant r world line, so that's accelerating, then that observer will observe the so-called Tolman temperature, which is related to this earlier temperature, called H, divided by the norm of psi. But this is not the fun fact. But the fun fact is that this, you can actually write this as a squared plus kappa squared divided by 2 pi. So kappa is the surface gravity I told you before, and a is the acceleration of this observer. So this term is due to the Unruh effect, and this term is due to the cosmological expansion. So in particular, if L goes to infinity, this goes to 0, and you get the Unruh temperature. Okay. Now, let me move to the second pattern. Thermodynamic laws. So what is actually a cosmological horizon? So it's often stated in the literature that it's observer dependent, but actually there's a more covariant way of describing what it is, and I wanted to briefly see that. So for a black hole, you can define a black hole event horizon by taking some time like geodesic lambda, and then there's an endpoint time like future infinity, and then the past of that endpoint is the black hole event horizon. Now, the boundary of the past. So this is the past, and the boundary of the past is the black hole event horizon. Now you can generalize this to other spacetimes, and in particular also to de Sitter space. So in de Sitter space, how do you describe a cosmological event horizon? You pick a point at scribe plus point P, and you draw the boundary of the past. So that's what a cosmological event horizon is. But now, of course, you can also pick another point and draw the boundary of its past, and that has a different, defines a different cosmological event horizon. And so this is the kind of observer dependence of the cosmological event horizon in contrast to the case of the black hole event horizon, which is unique. But actually, you could have picked a different point here, and then you also have a causal horizon here, but it's not the same black hole event horizon. Now, let me give one other example. In Minkowski space, you can pick any point and make a Rinter wedge in this way. So the fact that cosmological event horizons observer dependent is just the fact that it depends on this P, but the same applies to any causal phenomenon. Now, let me quickly state the zeroth law, which you probably don't know, is that kappa is constant on on any connected two surface in an event horizon. Yeah.
Typically, if you have a cry plot, which is space-like, rather than you would always get a customer.
Right.
There's something special in really consider space, which I mean, I guess what I want to know is there's something special about that. I couldn't take in any space now.
No, I
So
don't.
long as it has a crack plus, which is space like you have.
Okay, the only difference is that it has more properties, like it's a killing horizon in this interspace, so it's like more symmetric views. Yeah, so that's actually important also here. So this applies only to killing horizons, or stationary horizons. So psi is null. This means that psi is null on the horizon. And then briefly, the second law is just the area theory. So the area of a connected component of the horizon, cosmological horizon, never decrease. And this has been, I think, has been proven. This one, I'm talking this one. Okay, but I wanted to really focus on the first law. Because there is a funny minus.
It is not statement like saying that you cannot add matter to decrease the cosmological horizon. I mean, if for example, you compare.
Yeah, I will actually talk about this now.
Okay.
Yeah. Can decrease. I mean, if you throw something through the horizon, then it will increase. But if you put some matter, as you say, if you compare two geometries and you put some matter inside the static hash, then you will decrease the horizon area. That's what I want to say now. Okay. So the first, so if you take a for a black hole, you take the surface, then you can write down a you can vary the metric and matter fields. You can write down a first law. You can also include variations of the stress energy tensor. Called the matter Hamiltonian. Okay, but for the Sitter space, there is no boundary at infinity. So for the Sitter space, if you take this surface, then there's no ADM energy here at the pole. So the first law for the Sitter space has a zero there. Okay, and now if you take this to the both side, you get the minus sign. So this means if you put matter here, the area of the cosmological horizon actually decreases. And this is related to the fact that pure the Sitter space has maximum amplitude. Even if you create a black hole here, if you make a Schwarzschild de Sitter space-time, you cannot decrease this entropy. So for Schwarzschild de Sitter space, if you take the total entropy, the sum of the black hole horizon area and the cosmological horizon area, G, then this is always smaller or equal to the pure de Sitter entropy. Wait. So I can make a plot as a function of the mass for Schwarzschild de Sitter space. So this point is pure de Sitter, so for zero mass. Then if I increase the mass, get something like this for the for SC for the cosmological horizon area. So that decreases. So I put a black hole here. So this is the black hole horizon, and this is the cosmological event horizon. So they both have an area associated to them, and from various arguments, it follows that the total entropy is actually the sum of the areas. So here I only drew the area of the cosmological. Now, if you also draw the area of the black hole event horizon, then that increases if I increase the mass. There is a maximum mass. So that's the extremal black hole in de Sitter space. Sometimes that's referred to as a Nadia black hole, although that's a bit of a misnomer, because the Nadia geometry is this, so it's ds2 cross sd minus 2, which you get in the near horizon limits. Extreme this is just for extreme modes. In this case, the black hole event horizon rate is same to cosmological. And the total, so the total entropy is something like this, it's roughly a straight line in infinite dimensions. It is a straight line. But as you see, it's always smaller than the initial de Sitter entropy. So pure de Sitter space is maximal entropy. Now coming back to this first law, I want to understand what it means. The thermodynamic interpretation of this first law. So people have been confused, especially about this minus sign. And there were two proposals in the literature, one by Manus and Visser, and they just stated that the temperature is negative. temperature is minus the Hawking temperature. So they just incorporated the minus sign in the temperature, and then you get you get. I want to understand how this, first of all, really is. Now, in another proposal, in the Lazuche lecture notes on the Visser space by Strominger and Polovich and Spratin, where they is no actually the energy variation is negative. It's not that strange. So first, but it's not so strange. So what they said is the total energy on a global slice has to be 0. So if I integrate this on a global slice, it has to be 0, which means that on the right side it has to be equal to minus that on the left side. So for them, so this is like the right side. For them, this was like the Hamiltonian on the left side. And they said, well, that makes sense because entropy is also information, our ignorance about information behind the horizon. So we have to talk about energy behind the horizon. And let me also say what this kind of makes sense. So you do have negative temperature systems in nature, and they always have an energy balance, which in this case is given by this extremal mass. And you have about like a finite fluid space for bound on the entropy. And we also have that because we have a finite entropy. So, Ted Jacobson and I wrote a paper where we kind of just put this perspective. But then last year, we put out a paper together with Batul Badi Hashemi, who was a student of Jacobson, and Lisesco, who's now a postdoc in Belgium. And we gave a different proposal. So different things. And the what we did is we introduced a timeline boundary in order to define gravitational energy. So, we introduced this time-like boundary. Look at the distance between the horizon and the boundary. And Brown and York have done this for black holes, many papers on that. And Ted and the tools wrote a separate paper on this for cosmology. Now, why are we doing this? So in gravity, the energy on boundaries is you need a boundary to define an energy. So if there's no boundary, the energy is 0. So we wanted to define a proper thermodynamic ensemble and then take the limit where the boundary vanishes and then recover this result and interpret this result. So the result is very simple. The first law for this system with the boundary is takes this form. So this is very similar to what you find for black holes. If you have a boundary surrounding a black hole, so it's at some constant radius. So this is the area of the cosmological horizon. So this term is used. So what is this? This is the Brown-York energy. and it's associated to a cross section. D-2 sphere of this boundary. F. Let's take this form. So K here is the gravity expensive of the sphere inside the but. Oh, so this is standard thermodynamic first law. So this is the internal energy, this is the entropy, and this is a non-thermal contribution. In fact, if you have thermal matter, then you can write this as TdS, where now you have matter entropy as well. So then you get something like this. But now we want to study the limit where the boundary actually vanishes. And in that case, this energy vanishes. And the reason is that A goes as 1/r roughly in flat space. So if you're very close, looks like flat space. And dA goes like r to the d-2. And so this goes to 0 faster than this goes up. So it goes to 0. So in that case, you recover this previous first law. And so what is the conclusion? The temperature is finite. The energy, the internal energy is actually 0, which you could have concluded already from what I told you here. So the internal energy is 0 because there is no boundary. And this is a non-thermal contribution, and you shouldn't confuse this with the total internal energy. That was the confusion. So, yeah. Yeah, in that case you can have conical singularities actually, which represent point masses in the Sitter space. And they can I think they can have a finite groundwork energy, but that groundwork energy, if I'm not mistaken, is the same as that of pure Sitter space. So if you subtract the two, then I think it's still that. Yeah, for these two, GR is topological in these two, so you don't really have this definition. So if you have dilaton gravity in these two, then you can find something similar to this groundwork energy. And that will go here.
The same thing needs to happen if we take that time-like boundary in going towards the horizon.
Yes, okay, it's also a good question. So actually we'll come back to that later, but if you take it very close to the horizon, then so I didn't. There is actually a factor n here. So this is actually the related to the Tolman temperature.
What is it?
N is the norm. So this is actually the Tolman temperature, and this goes to 1 at the pole, but this goes up here. So I will come back later to this, but Susskind and motivated from black holes as well, thinks that the microscopic theory of the Sitter space is on the stretched horizon, where the temperature is actually very large, and then your system is kind of between the horizon and this stretched horizon. And this has implications. I will come back to this, but it has implications for what the state, the density matrix is associated to this data match in quantum gravity. Because it's been argued that it's maximally mixed. The time. All right. And now I want to move to the third evidence, which is the sphere partition function. And so I'll just briefly describe the work by Gibbons and Hawking. So they, of course, they're basically what this paper and derive the black hole entropy from the Euclidean path integral. But in the same paper, they also derive the Sitter entropy from the Euclidean path integral. Okay, so first you need to know that Euclidean d-dimensional de Sitter is a round B-sphere of radius L. And Gibbons and Hawking argued that the canonical thermal partition function in quantum gravity is related to the Euclidean path integral where you integrate over metric. And in the case of asymptotically de Sitter space, we want to integrate over compact positive curve, which is geometry. But in the saddle approximation, this path integral is dominated by the term where this is the action of the saddle. And so at the Sitter, you can show that the Sitter space is a global maximum. So it has minimal action, or in other words, it's minimal action or minimal volume space-time, Euclidean space-time volume. Okay, so now we want to compute the Euclidean action. So with a cosmological constant, we want to evaluate this on the Sitter space. And the computation is very simple. That's why I want to. So metric is just is. L to the 2 over get L to the D over the D. And from this term, we get 2 over. This is just, just have to compute the Ricci scalar. Okay, now we can use a formula that relates the volume of a unit D sphere that is related to the volume of a unit D minus 2 sphere. There are some 2 pi and minus 1. Then lo and behold, you get minus 8 as expected. So this is always the minus the Visser entropy. Now usually the Canadian action is related to the free energy divided by the temperature. That should be beta E minus plus. But we've seen before that E is actually 0 for the Visser space. And you also see that in this Euclidean case, because it's compact, there's no boundary on which to define E, so E has to be 0. Gibbons and Hawking already realized this. Okay. Now, I want to talk more about this. So let me first give some numbers actually, which is kind of fun. So if you reinstall all the constants of nature and you compute it for the Visser space, then you get 10 to the minus 10 to the 122. And so this is bigger than the entropy of all matter and radiation in the universe. So if you add up all the matter and radiation in the universe, then from what I've read is that this is dominated by the mass of supermassive black holes. And you get 10 to the 104. So this is much bigger. Now, of course, the big open question is what the microscopic origin of this entropy. And so could be 2 options. It could be a less one, it could be well, ideally we want to count the number of microstates in quantum gravity and reproduce this result. Like, for instance, Strominger and Baba string theory to count the black hole entropy of supersymmetric black holes. But we currently don't have such a similar computation, which is also related to the fact that supersymmetry is kind of hardening the Visser space. And the second option could be that it is entanglement entropy. And in induced gravity, this is precisely what happens. So if you have a quantum field theory and you look at some area, then the phenomenon entropy actually scales with the boundary of the subregion. But it's also divergent. You look at the generalized entropy, which adds up to the Visser entropy and the phenomenon entropy, then this is expected to be independent of epsilon of the UV cutoff. And this means that changing epsilon, this means that if you renormalize Newton's constant, then you also get epsilons, but those cancel against these epsilons. Now, if there is no bare Newton's constant, so in induced gravity, where gravity emerges, then both terms actually can originate from entanglement entropy. The fact that area and that's still the area is kind of suggestive. It could also be that both microscopic interpretations are correct. Maybe that in the UV you can count it this way, in the IR you can count it this way, and I will come back to this shortly, but recently entropy from a von Neumann entropy of an algebra of observables associated to the static patch. They kind of realized this. One other minor comment that I wanted to make is that you can compute one-loop corrections to this saddle point approximation. And there is a vast paper by Untitled Chapter and Sun where they compute this for many cases in many dimensions for many spins. And let me just give you a couple of results in their paper. Maybe there were previous results as well, but that's a very good reference. 2009. So in pure gravity in 4 dimensions, you get the log V is the leading piece, it's like entropy, but then you get -5 log. So this is a universal term, and then we get something, another log term that depends on the radius of the effective field theory. Now in PS3, in pure gravity, instead of this 5, you get a 3. So that number depends on the number of dimensions and also on the fields that are present. So if you have matter fields, then this number changes. But this number is usually, comes from the massless spectrum. And I think one reason to compute this or to talk about this is that if you propose a theory of quantum gravity, then you not only have to reproduce this result, but also the log terms. So if your log terms are incorrect, then you're in trouble.
One loop correction is obtained from the gradient calculation.
Yeah. And about the Visser entity, what more we can there was a conjecture by banks and then well, you gave a presentation about it. But yeah, they probably work together in mind. So the conjecture is that the de Sitter entropy counts the dimension of the open space in this way. If you put a black hole in the Sitter space, then you can see black hole. That means the freedom must be founded in the Sitter space. The third reason he gives is that different static patches. So you might say, well, this is only one static patch in the Sitter space. So if I take another static patch, then there might be more degrees of freedom. But they are all related by the Sitter isomorphy. And so hence you only count the degrees of freedom, one static patch. And in the path integral, since the space time is compact, you don't have a boundary, you should integrate over all the diffeomorphisms. And you don't have physical diffeomorphisms like you do in ADS, for instance, where you have physical diffeomorphisms at the boundary. Since Euclidean de Sitter is compact, you you will have to integrate over all these diffeomorphisms or isometries, and hence this kind of restricts the number of degrees of freedom. Okay. So I tried to look for this there. Arguments. Because of what? So the partition function in the saddle approximation, no, it's finite. No, it's e to the s.
Yeah,
Yes.
So one system usually.
Yeah, that's a surprising fact about quantum gravity. So, yeah.
So now it's saying that if the space of quantum gravity is fine.
Yes. Yes. Yeah. Good. Okay. Yeah. That's,
That's what it is to say. You and I, we both have our own right. Like that. Somehow we just only count your degrees of freedom, our somehow.
yeah. Well, you represent the degree of freedom in a different way, such that you have your cosmological horizon and I represent it in my way, but we both agree on the number. I mean, okay, this is a conjecture. Yeah.
This conjecture is not just about pure visitors. Right. I mean, you have any theory of gravity, possibly cosmological constant, whatever is the dimension of the.
Yeah, because
Because
how I
matter
interpret-
is not going to be.
yeah, exactly. Because otherwise it's just one state.
Yeah.
Um. Now there was this recent paper by Patrick. They to define a proper ensemble, they introduce a time-like boundary. So if you have a time slice of the static hash, then so this is the horizon, then they introduce some boundary here, and then they look at this system. So if you take the Euclidean time to be periodic, then this topology is at this time plus 2. And then they were interested in taking the limit where you recover the standards sphere partition function that I just described. And in that case, the topology changes and you get at because that is Euclidean Visser. Now, so we want to interpret this in case of where you have a time-like boundary as a canonical thermal partition function, where the temperature is like the temperature on this boundary, which is the atomic temperature. And the energy, the Hamiltonian is the boundary of the Hamiltonian. So it's precisely the energy on this boundary, which I described before. But in the limit where this boundary shrinks to 0 size, we saw before that the energy has to go to 0. So crucially, in that case, we get trace of 1. So the partition function is trace 1 over the entire Hilbert space. And if the Hilbert space is finite, this means that you count the Hilbert space, the dimension of the Hilbert space. And since this computation has we recover the projection. No, yeah, actually you don't. And in gravity, it's finite. So the Newton's constant that makes it finite. It's a non-perturbative calculation, of course. So yeah, I mean, I think for very long, I find this argument kind of convincing that that indeed e to the s is related to the dimension of the Hilbert space. By the way, this means that the that entanglement spectrum. So there was previous work by Silverstein, Dawn, and Photobau, where they also argued that the Sitter space should have a flat entanglement spectrum. Okay, so let me now come back to this stretch horizon, because in that case you can also recover this. So here I took the boundary to zero size, but what happens if I take the limit to the horizon? So if sort of R goes to L, then we saw before that beta has to go to zero. Temperature has to go to infinity, temperature, because you need infinite acceleration to reach the horizon. So in that case, you have the same result, you have phase one. And you have been, yeah. There is a difference though in the space time that you can cover, because here you cover the entire space time. Whereas in this case, you only kind of cover the space time in between the horizon and the boundary. But I think that these results are kind of complicated. And so, yeah, I think that this argument would confirm some of the statements that that's been making.
Can I think of the first one as a bulk calculation, the second one, rather interpretation of the first one as a kind of a bulk entropy, and the second one as the interpretation being of a graphic description?
I would say that both have the bulk, and I mean both. This is a bulk calculation, but in the end, the holographic dual should live at a boundary. So, yeah, whether it is here or there, that is kind of the difference. Yeah, since I'm actually running out of time, well, let me now skip to the brief comment on the holographic dual. And precisely talk about this point. So there are kind of two proposals in the literature about the holographic dual of De Sitter. So one is by Strominger, so the Sena, which is an ESCP correspondence. So which is saying that the holographic dual is as square plus and square minus. And the fundamental statement is that the wave function is related to the CFT partition function. But on the other hand, other people have suggested that think about the holography for the static map. And one reason is that in this TSP correspondence, it's hard to account for the entropy of the Sitter space. Whereas in the static patch, well, you have thermodynamics associated with the static patch, you should be able to, would be interesting to recover the entropy. So where does the holographic dual is? Well, it's kind of, I don't know, there is a, maybe it started with the world line holography by Aninos, Sean Hartnell and David Hoffman. They proposed that the holographic dual lives at the poles. And they found a hidden SL2R symmetry in the propagators, fractals and scalar fields. Now, Susskind has proposed that the dual gives us the stretch random. And as I said before, this is also motivated from black holes. And there is another paper by Silverstein, David Kong, and company of where they also suggested these. Yeah. Yes. Okay, so how,
That's polarizing. You could do that.
yeah, it's like a time-like surface that goes to the right.
Very close to the.
Like we planet is sensor. Area is less by 1.2. Yeah, I just wanted to make one comment about this, is that it could be that all of these proposals are actually correct, but there are somehow different representations of quantum gravity in the Sitter space. For instance, it could be that if I look at ADS-CFT, I can also, I mean, I could put the CFT on, CFT lives on the conformal boundary, but I can also move the CFT inwards, for instance, by graph deconversion or TP bar deconversion. So the UV of the CFT lives at the boundary, but the IR is in bulk. So the proposal would be that the UV lives here and the IR is at the horizon. But now, if I go inward inside the static patch, then again, I'm going towards the UV. So my main statement is that the holographic dual should live at some codimension 1 surface. So it could live here, there, and then on the horizon, then on the stretch horizon, then on some constant R surface, and then on the broad line. So in that sense, these different holographic topologies might be related by flowing in energy.
But do this UV and holographic dual, the two ways of computing entropy, are they at the UV and the IR?
Yes. Yeah.
And without using any supersymmetry somehow, you don't expect the E raised by E to be the same, do you? And there's no, you don't have any supersymmetry in the game at the moment, but you expect that the UV and IR.
So there is a more precise way of so in TP bar, and that's usually in ES or in ADS-CFT, but Silverstein has written papers on TP bar plus lambda 2, where he has an extra term that kind of moves you from ADS to the sitter. And then in that case, all these surfaces are related by this irrelevant deformation, and the energy changes, but the entropy stays the same. So that's how they know how they can calculate the entropy, because the energy lines don't cross. So the entropy stays the same. Right, then it's still here. Yeah. Where the other one would be. Yeah, I agree with that. But then you might ask how they are related. I mean, I can do a transformation from static patch to global coordinates. People have tried to reproduce the entropy in this framework as well, using asymptotic symmetries, for instance, in 3D. It's called the static patch. Choose to say, okay, it's great. Yeah, I agree with the statement. In the end, we find it very hard to relate them.
The pole can be anywhere. If you remove one pole, and another pole, or two.
Well, yeah, so with the static patch,
Yeah. Yeah. Last picture you mentioned, not that one.
Right.
Glasses,
Yeah,
we just take like ADS after,
yeah,
and there's this,
go inside the horizon.
right, that's right, going inside the horizon. What's called trans something, trans I,
Oh, right.
go an IR and then
Oh, yeah.
approach the singularity, then again come out, going to the mini spectrum.
Is that? Just, I actually don't know. Right? There are very few people.
I know strong things about
Right.
that language, in a way of trying to understand what that is.
They also suggest that you go back.
Maybe the truth is that we are going back to the, but in a sense you are. From the point of view of the forward life patch. Isn't it true that the horizon, from that point of view, is it true that the horizon is again IR?
Yeah, I think that's it. I would say that the horizon is.
I mean, typically horizon is a place where eventually you come
Right.
very large.
Right.
So in that sense, that's also
Yeah,
like you
Yeah.
reach one IR and then you cross.
I think in ADS-CFT it's not very well understood. But also if you go sub ADS radius, then what happens there? And sub ADS holography is not very well understood, and it could be that you go back to the UV. I have a paper on that, but get it put in and supervisor and something that actually where we also look at the sitter and suggest this reversal of UV ion.
I mean, all I'm saying is for the point of view of the comparative edge, it still makes a lot of sense.
Right. So the argument I present about the Byzantine wave is for any interacting sitter invariant on the field theory, but yeah. So you can also do a computation of field theory in this temperature in many different ways, but I don't know what the issues are here. Right there. I know there are many people have that the British rate is stable, but also Polyakov and Montola. But yeah, I don't have an opinion on this. No, yeah.
Starting from the visual theory, and taking it over scaling in. Then somehow you can reach point close to this reality. There's something that you can get dynamically. Let's see the horizon.
I think that's a conjecture by the assessment that some double scaling limit of SYK you get ES2 instead of ADS2. And as I said before, DS2 is the near horizon limit of NADI. But I don't think there is there substantive evidence for this. But it's a recent projection. Yeah, I don't. Yeah, well, actually, there's one paper which I actually haven't looked at is I thought was reference for example, and yeah, but I saw a talk by him about this, and he didn't even mention that part.
Yeah,
He just talked about double scale SYK, and then, whereas in the abstract it's very clear. Yeah, I think people will try to look for it.
I found that the scramble time is very small. In that keeping temperature double scale is what I did.
Okay,
Apart from that, that was one of the reasons for that project. If you consider, because again, from the stretch horizon. Apart from that, probably
okay.
pretty bad at the literature, but from my understanding is that if you take double scale this YK, that's very, very hard.
Right, which is,
Take
that is why you get those.
that,
Yeah.
that's why sort of getting towards the stretch.
Right. Right.
And you compute the scrambling time, that approach is real. So it's a super, what do you call, super fast scramble.
Right, hyper fast.
Okay.
So why is it for my and not it's for this scrambling? I think there's some
Or close to the, well, maybe you should ask about this.
It's a time that popped up kind of like the basic you have the light source and kind of whatever.
Yeah.
Yes.
Hi, Thomas.